Hi, I'm Yifu Yuan.
Hi, I am Dadian.
Today we're going to talk about our course project regarding the policy gradient in active learning of graph neural networks. Next slide, please. To begin with, I'll give a short introduction here. So we know that generally speaking, labeling data is very expensive. Active learning tries to tackle this problem by iteratively choosing the most valuable subset of data to label and trains the model based on this subset to achieve a good performance. On the other hand, graph neural networks are very popular in finding patterns in datasets with graph structures, and they have been an active research area these days. Then, Hu and others in their paper Graph Policy Network for Transferable Active Learning on Graphs applied reinforcement learning in active learning of graph neural networks. They propose that the active learning process can actually be formulated as an MDP problem where the state is the stacked feature and matrix vectors of each node. The reward is a classification accuracy after each epoch, and the action is to choose the next unlabeled node to label. Later, we will formalize our definition on this MDP problem later. Next slide, please. Now, we're going to give the problem definition. The setup is very general in GNN. We have a graph with edge set and node set, where the node set is partitioned into three sets: training set, validation set, and a test set. In addition, we initialize an empty node set L with a budget B as its maximum size. The goal is to train a classification GNN using the set L to classify the nodes in the test set. The method here involves reinforcement learning. In each step, we'll use policy network to choose the most valuable node in the training set and add it to the set L as if some oracle labeled it for us. Then, we train the classification GNN using the updated set L. After the budget is used up, we simply train the classification GNN using the set L until convergence. Next slide, please. Now we will formalize this MDP problem. We follow the same framework of Hu, and others in their original paper. We will talk about the state representation, action, reward, and transition dynamics. Next slide, please. First of all, the state representation of a graph G at step T is represented as a matrix S, where each row is the state representation of each node. In the original paper, there are four heuristics connected together to form a state vector for a node: degree of a node, entropy of predicted label distribution by the classification model, class probability predicted by the classification model, and a 0-1 indicator variable representing if a node is added to the set L. Next slide, please. Secondly, the action at each step is just to select the most valuable node and add it to the set L based on the action probability given by the policy network. The reward is very simple. It's just the micro F1 score of the classification model after the convergence. The transition dynamics are hard to define, but we know that in each iteration, the set L is updated. As the model is trained on the set L, the classification model is also updated. Hence, the state matrix S is also updated, so we move to the next state in each iteration. Next slide, please. As for the policy network, instead of using MLP, another GNN is used to exploit the high correlation of graph nodes. At the end of the network, a linear layer with output dimension of 1 is added, followed by a softmax layer. These two layers act to be the action probability extractor for every node. Next slide, please. Here is a general workflow of this method. On the left-hand side, we have our state matrix S. We feed it as input to the policy network to retrieve the action probability at each step. Then we simply select the most possible node and add it to the set L. And we train the classification model using the set L. Then we check if the budget B is reached. If not, we move back to the protocol again by starting with the updated state matrix S. Otherwise, if the budget is used up, we train the model to convergence and use its final micro F1 accuracy as a reward to update the policy network. Next slide, please. After we have discussed the problem definition and the origin setup, my teammate Dadian will talk about our adjustments and experiments.
We used the same framework as Hu and Sean and etc. Under this paradigm, we investigate the following topics: whether better state representation is able to offer better policy guidance, whether abandoned rewards will be better than sparse rewards, whether more advanced policy gradient algorithm will improve the performance. In the evaluation of our adjustment and experiment, we use the same graph in the original paper, which is Reddit 1, 2, 3, 4, and 5 graphs, which are collected from Reddit forum, where each node in each graph belongs to one of 7 classes. We train the policy network using Reddit 1 and Reddit 2, and evaluate the policy network on Reddit 3, 4, and 5. The metric shown afterward is the micro F1 score of the classification test. We revised the state representation. Besides the original 4 features, we added the following 3 heuristics. Firstly, the page rank centrality is widely used in graph-related tests to reflect the node's connectivity and importance in terms of incoming links. The equation is shown here, where A is the adjacency matrix and P is a damping parameter. Secondly, we propose feature dissimilarity score to reflect how different is a node to others. We use the inverse of feature inner product to get such score. Thirdly, we propose structural dissimilarity scores to account for connectivity of nodes using the square of adjacency matrix, whose I and J entry represent the number of length works from node I to node J. This heuristic combined will balance the next node choice between connectivity and dissimilarity. In other words, the next node will be balanced in both topological importance and a bit of merit in terms of feature distribution. Therefore, we can expect such node to be valuable and informative to classification GNN training process. Hence, we expect the state representation will also have a better, will be better and also more sophisticated. And here is the result of using better state representation. The original in the table means for original heuristic, while better state representation is after adding 3 additional composed one. The backbone algorithm used here is Valina reinforced. The results shown are micro F1 score of the classification test. And then we also investigate like sparse rewards versus abundant rewards. In the original setting, the reward are the micro F1 score of the classification GNN after convergence. Thus, the rewards are sparse. We experience using the micro F1 score at each step after updating set L. Therefore, the reward will be abundant, but it will suffer from the variance of GNN and hence affect the training of policy network. Here is the result of sparse reward versus abundant reward. The first 2 columns represent the resulting micro F1 score using sparse and abundant rewards, respectively, subtracting a baseline. The last column represents the micro F1s using abundant reward, but no baseline to reduce variance. Here we can see that the impact of the variant of GNN is huge, since after we include baseline, like the performance improvement is huge. Then we also try some other reinforcement learning backbone. Hu and Sean use vanilla reinforced as policy gradient backbone. We try some more advanced policy gradient backbone. What we have tried is advantage actor critique and PPO. Advantage actor critique use a critique network to estimate advantage function and update policy with the advantage function. The use of advantage reduces the variance and is beneficial for policy training. PPO is an algorithm that has been widely used on many reinforcement learning tests and is one of the state-of-the-art algorithm. PPO or our overcome training failure caused by large step update by imposing a trust region through the use of cliffs and the ratio of old and new policy. Here is the result. Here is a comparison in performance between PPO and AAC and the vanilla reinforced. As we can see, the improvement like from vanilla reinforced to AAC is huge. This is because vanilla reinforced use Monte Carlo way to get expected reward and use that reward to update the policy. However, advantage actor critique use a critique network to estimate the advantage, and the advantage is the Q value subtracted by the state value, and this will reduce the variance of GNN. And as we can see, by reducing the variance, the improvement is huge. However, there is only minor improvement from advantage actor critique to PPO. So we can say that in this text, the last step update failure is less likely to happen. So in conclusion, we can see that using better and more sophisticated state representation can be beneficial to reinforcement learning. And adding baseline can be of huge impact, especially when GNN accuracy is hugely variant. And we also get some hands-on experience in working with various policy gradient algorithm. And we can see that the policy gradient that reduce the variance is helpful for this GNN network. And that's all for our final representation. Thank you.